linear systems of differential equations. What we mean by this is a system of equations which are linear, but they are linked. So if you look at this pair here as a simple example, we've got the derivative of x with respect to time is equal to y, and the derivative of y with respect to time is minus x. So we can see that they are linear, there's no squareds or products x times y, and obviously we can see their differential equations. The question is, how would you go about solving them? You might like to pause the video while you have a think. Overall, the method is reasonably straightforward. What we do is we eliminate y to get a differential equation in x, but because that y occurs on its own and differentiated, the equation we get will be a second differential in x. Okay, so we differentiate our equation 1 to get this equation here. Okay, we can then replace dy by dt by minus x, and suddenly we've got our equation of simple harmonic motion that we looked at in previous videos. And we know the solution to that. Here in particular, the angular frequency is 1, so the solution is a sine t plus b cos t. But as with any set of simultaneous equations, whether they're differential or normal, we haven't finished because that's only x. We need to work out how y varies with time. Okay, how does y vary with time? Well, we just substitute that back into equation 1. Okay, rather simpler than, by the way, than substituting into equation 2. So we have to differentiate x, and then we get our final answer. And notice that therefore, when we work out a and b using probably initial conditions on the values of x and t, that will then give us the values of a and b for both x and y. That was a rather simple example, so let's look at a slightly more difficult one. Here we can see that our two equations, in both cases, the rate of change of x and y depends, each of them, on the values of x and y. Now, if these were just normal linear equations, the temptation would be to either add the equations, which would eliminate y, or subtract the equations to eliminate x. But we'll still be left with the differentials on the left-hand side. So now comes the question, what would you do with these equations? Again, you might want to have a pause the video while you have a think. So we're going to eliminate y and again get a second order differential equation in x. Okay, but we have to eliminate not just y this time, but actually also dy by dt. So the method we use is very similar to the one on the previous slide. Okay, we differentiate the top equation, and that gives us our dy by dt. What do we do then? Well, we eliminate dy by dt using equation 2. But now we've got a y coming back in again. How is it going to eliminate y without introducing dy by dt? By using equation 1 again. And then we get our new second order differential equation. In this case again, it's simple harmonic motion. In this occasion though, the angular frequency is going to be the square root of 2. So that's got the value for x. We can now substitute x back into either equation 1 or equation 2. And as with all these substitutions back in, one of them's easier than the other, but in this case, much easier. Yep, that's right. We substitute back into equation 1 because it's only got a single y in it. We don't have to worry about integrating again. So we do that. We differentiate dx by dt. We can then substitute in, work out the value of y, and there's our rather inelegant looking solution. Obviously, again, once we have our initial conditions, then we can work out the values of a and b. So that is the principle of the linear systems of linked differential equations. Obviously, I haven't gone through yet an example where we have to work out the values of A and B. I'll wait for someone to email me requesting a work solution to one of those sorts of problems, and then I'll provide a new video for that. I'd also like to point out that actually the idea of linked differential equations but non-linear is very important. I'm going to be producing a separate video on that, looking both at what is in the A-level textbook, whether they look at population dynamics, but also epidemic modelling, very relevant at present, and the SIR model, which is basically 3 linked non-linear differential equations. As ever, if you've got any questions or queries, just feel free to email me. Thank you very much for watching.